In the last couple of lectures, we focused a lot on square matrices. We saw that every square matrix can be triangularized, that is, every square matrix is similar to an upper triangular matrix. We also saw that every square matrix is block diagonalizable, that is, every square matrix is similar to a block diagonal matrix where each of these blocks is governed in some way by the eigenspaces. And some matrices are diagonalizable, that is, these matrices are similar to a diagonal matrix, but throughout we assume that the matrix in consideration was square. Now what happens if a matrix is rectangular? Can we always can we write this? There's no notion of similarity any longer, but is it in some sense, can it be converted to a diagonal matrix? And that is answered by the topic of today's lecture, which is singular value decomposition. So going right to the statement of singular value decomposition, any m by n matrix A, for now we'll assume that the matrix A is real valued. So any real valued matrix A can be written as U times D times V transpose, where U and V have orthonormal columns, and D is a diagonal matrix where all the diagonal entries are strictly real and are positive or zero. Right? So D is not really a square matrix. It could be it's a rectangular matrix in general. It's an m by n matrix, and the number of non-zero elements in D is equal to R, the rank of A, and the R non-zero elements occur in the principal diagonal, and these are called the singular values of A. So typically the singular values are written in the decreasing order, so sigma 1 is greater than or equal to sigma 2 and so on, and sigma I is called the ith singular value of A. And the columns of V are called the right singular vectors of A, and the columns of U are called the left singular vectors of A. So the V corresponds to right singular vectors, and U corresponds to the left singular vectors, right? So what is important to note here is that note that when we talked about diagonalizability of a matrix, even though we had a real matrix A, we noted that some real matrices can have complex eigenvalues. However, the singular values are always real valued. In fact, even if we consider an arbitrary n by n complex matrix A, complex valued matrix A, then you can write this as U times D times V Hermitian. So the Hermitian is simply the conjugate transpose, where U and V could be complex valued, but D is always real valued and the singular values are always non-negative, right? So that's the speciality about the singular value decomposition. So now let's see what is the geometric interpretation of the singular value decomposition. So basically what are we doing? We're first doing an orthogonal transformation by V, and then we're doing multiplying by a diagonal matrix, and then multiplying by another orthogonal transformation U. So any matrix can be represented as a series of transformations. The first is basically a rotation, right? So V transpose corresponds to a rotation. D corresponds to scaling, so you scale along each of the coordinate axes, and U corresponds to another orthonormal transformation, which you can think of as a rotation. So this is very nicely captured by the Wikipedia page on singular value decomposition. So here's a nice animated illustration. So given any matrix A, you can always represent it as a series of three transformations, which is a rotation, scaling, and another rotation. So suppose that we have a matrix M, then you can this matrix can be considered as, so you take the unit disk, right, and then you first rotate it and then scale it, right? So you have this, so you first rotate it and then you squish it by sigma. So sigma is a diagonal matrix, right? And then U is the third transformation, which is another rotation, and this gives you the matrix. Okay, so that's the geometric interpretation, but there's also another way of interpreting the singular value decomposition, in the sense that the singular value decomposition arises naturally in a different problem. Right? So the problem is as follows. Suppose that we are given m vectors in Rn. Okay, so suppose, let me call them a1, a2 up to am, a1, a2 up to am. I have m vectors. So you can think of these vectors corresponding to the m rows of a matrix A. A1, A2, AM. Right, so these are the rows of the matrix. So the goal, given these m vectors, the goal is to find a k-dimensional subspace of Rn, which is in some sense closest to this set of m vectors, right? And by closest, I mean that this minimizes the sum of the square distances to these vectors. Let me be a little more precise. So given these vectors, I will define the squared error ei squared. So suppose that we are given these vectors a1 through am, and we have an arbitrary subspace W. Right? The squared error, or the square distance from ai to W, squared distance, or sometimes you can call it the error between ai and the subspace W, is ei squared, which is defined as the minimum over all vectors v in the space W of the square distance between the two, ai minus v the whole square. So this is the square distance between ai and W, and the goal is to find a W which minimizes the sum of the square distances, right? So the goal is to find the W of dimension k, which minimizes the sum of the squared errors. Right? So let's look at this using a more simple example. Right? So suppose that I'm given 3 points in R2, so A1, A2, and A3, and my goal here is to find a straight line passing through the origin which minimizes the sum of the squared distances to this line, right? So corresponding to so in other words, the goal is to find the best straight line passing through the origin which approximates these 3 points. right? So if I call E1 as the distance from A1 to this line, and A2, the E2 to be the distance from A2 to this line, and E3 to be the distance from A3 to this line, I want to find this blue line which minimizes E1 squared plus E2 squared plus E3 squared, right? So this is what we want to minimize, and any line can be represented by can be uniquely represented, can be represented by an orthogonal vector, or sorry, a normal vector v, right, of unit norm. So basically you represent this line by a direction vector. So the goal is to find this vector v of unit norm, which minimizes the sum of square distances to this line, right? Now it turns out that instead of looking at the sum of the squared errors, it's easier to look at the projections, right? So effectively, now this is something that you've already seen when you were basically looking at least square solutions to linear systems. So instead of so minimizing the square distance is basically equivalent to finding the projection, right? And simply put, minimizing the sum of these squares turns out to be equivalent to finding that vector v which minimizes the sum of the projection, sum of the length of the projection along the direction v, right? So in other words, minimizing E1 square plus E2 square plus E3 square is equivalent to minimizing these projections. So this is the first projection, this is the projection of A2, and this is projection of A3, right? So basically you want to minimize the sum of this green line, the length of the green line, the red line, and the yellow line, right? And this easily follows from Pythagoras theorem in some sense, because the sum of the absolute value of this projection, or the sum of the square of the projection, is essentially, so maximizing the sum of the squared projections is the same as minimizing the sum of the squared errors, or the minimum or minimizing the sum of the squared distances, because the length of this projection is basically the difference between the length of A1 and E1 square. So if I call this green vector as, say, beta 1, then just by Pythagoras theorem I have that norm A1 squared equal to E1 square plus beta 1 square. Similarly, norm A2 square equal to E2 square plus beta 2 square, which is the length of the red vector, and A3 squared equal to E3 squared plus beta 3 squared, where beta 3 is the yellow vector, right? And since E1 square plus E2 square plus E3 square plus beta 1 square plus beta 2 square plus beta 3 square is a constant for given A1, A2 and A3, maximizing E1 square plus E2 square plus E3 square, sorry, minimizing E1 square plus E2 square plus E3 square is equivalent to maximizing beta 1 square plus beta 2 square plus beta 3 square, right? So you can prove this a little more formally, and I won't get into the details of this proof, but basically minimizing the sum of square distances is the same as maximizing the sum of the absolute values of the projections, or maximizing the sum of the squared projections. But look at this term on the right hand side. Look at this particular term. Can you tell me what this is equal to? So this is essentially A times V squared. So the norm squared of A times V. Right? So at least in one dimension, the problem of this problem of minimizing the squared error, sum of squared errors, is equivalent to finding a unit vector V which maximizes the norm squared of A times V. Right? So in one dimension, this is A times V. Right? So basically what we'll do for larger K is the following. So essentially, for larger K, what is our goal? Our goal is the following. So find orthonormal vectors V1, V2 up to Vk. So this corresponds to an orthonormal basis of the W that we are looking for, such that, or which maximizes the sum from 1 through K of AVI the whole square. Right? So this is going to be the goal. Right? So in other words, our goal is to find the best K-dimensional space which approximates our matrix, right? Our given set of points, right? So we're given M points, and our goal is to find the best fit plane or hyperplane in K dimensions, right? Or K-dimensional subspace, to be more precise, right? So instead of finding the space directly, let's look at a greedy algorithm for finding such a solution, right? What we'll do is, we know how to solve it in one dimension, right? So in one dimension, you find a V1 which is of unit length and maximizes the norm squared of A times V, right? So we know how to solve this particular problem. So what we do is, instead of collectively trying to find K vectors at once, so once you first find V1, then I'll find a V2 which is orthogonal to V1 and it has unit norm and maximizes AV the whole square, right? And I'll keep repeating this. So I find a V3 which is orthogonal to V1 and V2 and has unit norm but maximizes the norm squared of A times V, right? And so on all the way up to K, right? So I'm not exactly solving this problem. Well, I don't know if I'm really solving this problem, but I'm trying to maybe find an approximation. So maybe it's easier to do this. But it turns out that this greedy algorithm, so the V1, V2 up to Vk that I get, is precisely the one which maximizes this. Again, I won't go through the proof over here. It's basically an induction argument, and at the end of this lecture, I'll add a reference where you can go through the detailed proofs. Right? So basically, what we have now is a greedy algorithm for finding an orthonormal basis, which minimizes, which is kind of a best K-dimensional approximation of M points. So we're given M points and now we have a k-dimensional subspace or a k-dimensional approximation of these m points, right? And basically, and how is this connected to the singular value decomposition? It turns out that the v1, v2, vk, and so on are basically the right singular vectors. So I'll call vi as the ith. So the vi obtained using this procedure is the ith right singular vector. The corresponding value of norm AV squared, so norm AVI, which is a positive quantity, or at least a non-negative quantity. So this is what I'll call the ith singular value, right? So the VI's are the right singular vectors, and the norm of AVI is the ith singular value, right? So let's ask ourselves the question: how far can we proceed? So I have this greedy algorithm for any arbitrary k, right? So can I go on all the way up to m, or do I have to stop somewhere before that? So it turns out that I mean, you can convince yourself of this, that if R is equal to the rank of A, then the corresponding norm AVI, so at the I plus 1th step, so at the R plus 1th step, norm A it turns out that the max of all overall V, such that V is orthogonal to V1 up to VR, right, of the norm of AV, this is equal to 0. And the reason is because since R is the rank of A, you would have already found a basis for the subspace which contains, or a basis for the row space of A. So V1, V2 up to VR form a basis for the row space of A, and any vector which is orthogonal to this is going to lie in the right null space, and therefore the norm of AV is going to be equal to 0, right? So beyond R, the singular values are all equal to 0. So I'll denote each of these AVIs. So I'll call sigma I to be the ith singular value, right? So sigma R plus 1, so on, sigma M are all equal to 0, right? Right. So, but on the other hand, we can naturally extend this to a basis for Rn, right? So know that each of these vectors is in Rn, and now since we already have V1 through Vr, which basically are in the row space of A, you can consider a subspace. So you can consider the null. You can consider an orthonormal basis for the null space of A, and then you can combine this with VR to form an orthonormal basis for Rn, right? And this basically corresponds to the right singular vectors. So these vectors V1 through Vn, right, this corresponds to the matrix V in the singular value decomposition. So we've now seen singular values and the right singular vectors. What about the left singular vectors? So it turns out that if I define ui to be a times vi divided by sigma I, then the ui's, these vectors ui's, u1, u2 up to um, are orthonormal to each other, right? So here, of course, I'm only considering u1, u2 up to ur, the rank, right? Because after all, only so avi, so only the first r sigma r singular values are non-zero. Beyond that, it doesn't make sense. So u1 up to ur are all orthonormal to each other, and they're called the left singular vectors. Right? And given this, since the ui's and vi's are the ui's form an orthonormal set and vi's form an orthonormal set, you can verify that the matrix A can be written as a summation from I going from 1 through R of sigma I ui vi transpose, or that each of these ui vi transpose is a rank 1 matrix. So effectively we are finding so we are representing, so this is essentially a representation of A as a sum of R rank 1 matrices, right? So R m by n rank 1 matrices, and if you truncate it up to K, so instead of looking at I going from 1 through R, if you stop at some K for K less than R, then it turns out to be the best approximation for A, the best rank K approximation for A, right? And we'll just revisit that in a moment. But before that, a very useful property is that the sum of the squares of the singular values of A is equal to the sum of the squared entries of A, right? And this is called the squared Frobenius norm. The Frobenius norm of A. So the sum of the squares of the singular values is equal to the Frobenius norm of A. And as I just mentioned, the best rank K approximation of A, which is defined as a rank, so we say that B is a rank K is the best rank K approximation of A if B is of rank K and it minimizes the Frobenius norm squared of A, right? So this is the Frobenius norm squared of A, and our goal is to find a rank K matrix which minimizes the squared Frobenius norm of the difference, right? And that turns out to be this AK, which is obtained by essentially by finding the singular value decomposition and setting all the k plus 1, k plus 1, k plus 2 all the way up to R, all those singular values to 0, right? So again, I'm not going to do any detailed proofs in this particular lecture. For detailed proofs, you can take a look at this book called Foundations of Data Science by Blum, Hopcroft and Kernan. This has a very nice chapter on the singular value decomposition, and I'll also add a reference on Piazza, right? So we've seen we've seen two interpretations of the singular value decomposition. One, a geometric interpretation. So every linear transformation can be written as can be obtained by first taking a unitary transformation and then a diagonal transformation, which is basically a scaling, and then another unitary transformation. So rotation, scaling, and then another rotation, right? And we've seen another interpretation, that is the singular value decomposition arises naturally in trying to find the best rank k approximation of a matrix, right? But this interpretation is not very useful in actually computing the singular value decomposition. So it's maybe useful to look at some of the concepts that we've seen in previous lectures and use the ideas here. So we now know that any matrix A, any rectangular matrix A, can be written as U D V transpose. We'll assume that the matrix A is real valued. So A can be written as U D V transpose, where U and V have orthonormal columns, right? And our goal is to find U, D, and V for a given A. Now let's look at A transpose A. Right, so what is this equal to? This is equal to V D square V transpose, right? Where D is a diagonal matrix, right? And the entries are the squared singular values, right? So if we want to find V, all we need to do is an eigen decomposition of A transpose A. Right? And we know how that this can be done because A transpose A is symmetric and positive definite. It's symmetric and positive semi-definite, right? And therefore we know that A transpose A is orthogonally diagonalizable, and the matrix V basically corresponds to the orthonormal eigenbasis, right? So now we know how to do this. So A transpose A is V D square V transpose, and the columns of V basically correspond to the orthonormal eigenvectors, orthonormal eigenbasis for A transpose A. And D squared and the eigenvalues of A transpose A are basically the squared singular values. So now we know how to obtain both V and D, right? Now we can write V as V1, V2, where V1 is an n by R matrix. R is the rank of A. So these correspond to the non-zero singular values, right? And the matrix V2, the submatrix V2 is n, has n rows and n minus r columns, right? And these correspond to the zero singular values, right? So similarly, I can also write U, which we still have to find, as U1, U2, where U1 is m by r and U2 is m by m minus r, right? And it's not too easy to show that if D, I can also write D as, say, D prime and then 0, right? So all of those are 0. It's not too difficult to see that you can write A, which is U D V transpose, which is the same as U1 D prime V1 transpose, right? So D prime is an R by R diagonal matrix with non-zero diagonal elements, and U1 is m by r, D prime is r by r, and V1 is n by r. So V1 transpose is r by n. So overall we get an m by n matrix, right? So this is equal to, so A is equal to U D prime V1 transpose, and therefore we can obtain U1, by solving a system of linear equations. So this essentially corresponds to solving a V1 D prime inverse. So that gives us U1, right? And then we can extend this to an orthonormal basis to get U2. So U2 is any set of m minus r vectors which are orthogonal to all the vectors in U1. Right? So this is kind of an algorithm to find the singular value decomposition of a matrix. Now in practice, like packages like MATLAB or Python use numerical algorithms to find the singular value decomposition. They don't really solve all of these systems of linear equations. And again, some of these details can be found in this reference by Blum, Hopcroft and Kannan.